to show you the properties of the Fourier series on the example. And so we examined such signal at the beginning of these presentations, and now we have the shifted waveform with the quarter period shifting, and because this coefficient corresponds to a phase shift in the Fourier series, the original functions with the angle shifted by amount directly proportional to frequency. Okay, and so we must remember, this is the most important information, that time shift in the time domain corresponds to phase shift in the frequency domain. Okay, and so we have the original functions and shifted functions with this shift, and time delay. We can calculate this time delay. It is connected with this shifting. And now we use the property number 2 for this. So we can multiply our coefficients from original functions which we have by this coefficient. Okay, and now I calculated this one, n omega td, and when I put this value, I obtain n by multiplied by 90 degrees. Okay, so we know that the original from the coefficients from the original functions we can multiply by this factor. So the original functions is here, and the shifted waveform should be in this form. So we see the coefficients. Okay, and in the time domain we have to summarize this from original, and for shifted function it is the same, but it is changed in the phase. So there is the differences. Okay, and now we can try to calculate coefficients directly from the waveform using the definitions, and this is similar to the as we make this previously, and we obtain such coefficients. And these coefficients, we have here the j, and this j I write as a e up to minus j 90 degrees. And since n is odd, we can show that this expression is equivalent the expressions which we obtained earlier. Okay, and now I show you the properties of Fourier series, the example connected with the delta and with the integration, differentiations. Sorry. And because it's not obviously, sometimes we can use some tricks for calculate the Fourier coefficients, and so we have such signals. Here is the ramp, and this is the constant amplitude, and this is the one period. And okay, and so we take into account this one period. Okay, and we can try to find this Fourier coefficients. So firstly, we can derivative this signal, and as a result, we obtain here the constant value in this region, and from derivative for the constants is equal 0 from this, and here, because it is the rapid here, rapid change here, we obtain here the delta functions, and this amplitude, because here we have the v amplitude, we obtain the minus v multiply by delta t, because it's changed from v to 0. And we know that when we make the differentiation, we obtain, we know the differentiations of this function. We can multiply by coefficients by this factor jn omega 0. And now we can write this function when we subtract this delta from this function, because we cannot make the differentiation of the delta, but we can subtract from this one, and we obtain the g function. G function is the function of this picture without the delta. So we know, and now we make the differentiation of g function. Of course, we remember about this delta, and we know that the differentiation of the g function is equal a n c n plus 1t multiplied by v. It is connected with the delta transformation. Okay, and so we have this one, and after differentiation we obtain this. When we differentiate this signal, we obtain 2 delta here, and on the left side we can write the firstly, this is the first delta, this is the amplitude, and this is the transformation, and the second delta, it is it has the opposite amplitude, and it is also shifted in time. So we write these coefficients here, and because we make the differentiation the second time, this coefficient is arrived here, and here is the original from the first differentiation. And when we have such function, we can try to calculate Cn from directly from this, because we have, say, Cn here, and for n not equal 0, and this is the average value of this function. So when we use the properties connected with differentiation and with the delta from such signal, we can calculate the Fourier coefficients in this way. Okay, and now waveform generation. So the first information: the magnitude of harmonics in a Fourier series is independent of the time scale for a given shape. The equations for a variety of waveforms can be given in tabular form without expression a specific time scale. And the level of wave can be adjusted by changing the levels, can be adjusted for changing the average value. So we can shift all functions up or down using the DC value. And the time can be shifted by adjusting the angle of harmonics. So DC is connected with the y-axis with the function, and angle is connected with the time axis, x-axis. Okay, and 2 waveforms can be added to produce the third waveforms. It is directly from the properties of Fourier coefficients, the first property. Okay, so we have some expressions for typical signals using in electronics, and so I give you this functions here. And for example, for this signal, we have such expression, and sometimes this expression is connected with the n odd and even type. Okay, and so maybe I omit this because we cannot time for this. I just give you, because it is useful in practice or in laboratory. You can also use this. And so it's the touch signal, and on this signal we calculate this, and this signal is it is the full rectified signal, which is connected with supply, and half rectified signal and its harmonics. For example, we have here the even harmonics in this signal, and it's the triangle signal, sawtooth, and some assembly functions, and different type of sawtooth. And this is the differences is only in the sign of amplitude here. And for example, this functions when we have the changing connected with the exponential, changing amplitude connected with the exponential functions. Okay, and now we are talking about the frequency spectrum. Frequency spectrum, it is the very useful in laboratory. And frequency spectrum consists with amplitude spectrum. So we have the spectrum, frequency spectrum can be expressed as a Fourier series consists of a plot of amplitude of harmonic versus frequency. So here we have the number of harmonic. Here we have the number of harmonic. We can also show as a function of frequency, because n is connected with the frequency. And phase spectrum. So the frequency expressed as a Fourier series consists of plot of phase of the harmonics, of course, of harmonics or frequency. Okay, and since the frequency component are discrete, the spectra are called the line spectra. Such spectra illustrate the frequency content of the signal. Okay, and this is the result of amplitude and phase spectrum for such sawtooth signal. Okay, and now you have the example of the Fourier series triangular type waveform with such amplitude, and so we have here we see the assembly of such signals and this one and this one signal. So it is given by summarize this signal and this one. So, and we can plot the first form terms of the amplitude and phase spectra for this signal. So we have the components connected with the sinus and with the cosinus. We know that the cosinus is connected with the an factors and sinus with bn coefficients. Okay, and we remember that the relationship between C coefficients and A and B and coefficients, which is connected with trigonometrical form of a Fourier series, and with the amplitude dn. Okay, so on the plot we show the dn. So we can directly from this one we can calculate the dn. So we have here the an, and it's first d1. It is for n equal 1. Okay, and for 1 it is here we have the 1, and we have just the 40 by t squared. for this, and the same for this one. But of course we can put here the j because it is connected with the imaginary part. Okay, and we change the form complex number to the amplitude and the phase for the first harmonic, and we make the same for the third, for the fifth harmonic, and for the seventh harmonic. And now we can plot this, so for the first we obtain more than 7.5. For the frequency, triple frequency, we obtain such amplitude, and the same for this one and for this one, and the same for the phase. So we see here the phase minus 122, and we plot this. And the similar for the rest of coefficients. Okay, and now we have the example of frequency spectrum. We can imagine that we have the square waveform generator operating at 1 kilohertz and as a source, and we wish to design the notch filter that we eliminate, for example, first, 5, and 7 harmonic from this signal. So the simplest filter is the notch filter. It is the LC resonant circuit in the series LC branch, because you know that at the resonant the impedance is equal 0 for such circuit. Of course, we have here the resistor because we cannot short the source, and now we try to design filters for this. We choose, for example, one inductor and calculate the capacitance for the capacitors. It is the good idea because it is simpler make the several value of the inductors, but it is we have the whole range of the capacitors. Okay, and now we make the whole schematic. So we have our source with some resistance, and we have the notch filter, which is called also the trap for the first, for the second, and for the third frequency, respectively to 3, 5, and 7 kilohertz. Okay, and now we can make the simulations, and when we eliminate from this signal this one, we obtain such signal which is similar to the sinus. Of course, when we eliminate another harmonic, we obtain more similar signal to the sinus, to the first harmonic, the base signal. Okay, and now we are talking about the steady-state network response. So, if any periodic signal is applied to a network, the steady-state voltage or current of in this circuit can be found in this procedure. It is very important because it is the reason why we calculate the Fourier coefficients, and transform for the Fourier. Okay, so firstly, we have to represent the periodic forcing function by a Fourier series. And so, if the input forcing is a voltage, that the input can be expressed in the form, for example, as a summarize of the voltage, and voltage source should be connected in series. When we use the current, we can current source, we should connect it in parallel. Okay, and each source has its own amplitude and frequency. So this is the formalism, but I showed you previously on one of the simulation when I use such source in series, and determine the response due to each component of Fourier series. So we can take to account separately sources. So we determine the response, for example, from the first sources, after for the second, third, etc. And use, of course, the phasor analysis. We can use the phasor analysis because we have all sources are the sinusoidal sources, sinusoidal type sources, and transfer the network response due to each source in the frequency domain to the time domain. And function solutions, each source using the principle of superposition to obtain the Fourier series for the steady-state network response. Okay, and now we are talking about the average power. Average power, we have the voltage and the current in our system, and when we write the equations for the power, we know about there is the relationship between voltage and the current, but the integrand in this case involves the product of two infinity series, because we have the infinity series here and here. But firstly, DC and VDC and IDC over a period are divided by period is simply VDC multiplied by IDC. And VDC and any harmonic of current or IDC and any harmonic of the voltage when integrate over a period give us the zero, and the product of any two different harmonic of the voltage and current when integrated over the period always is equal to zero, and non-zero terms results only from the products of voltage and current at the same frequency. So we can when we take to account these four properties, we obtain the equations for power. Okay, and so in these equations we see also the infinity limit here, but we have here also the differences in phase in the cosinus here. Okay, and so now 2 examples. First, we should determine the steady-state voltage V0 t if the input voltage is given by the expression. Okay, so we have the expression which describes the sources. The source, and the source has no constant term, and therefore its DC value is equal 0. And so we can write in the time domain the amplitude for this. And from the network, when we use the phasor analysis, we know that the current, which is flow here, is equal. So instead of this resistor and this resistor, they are connected in the series. We should use the one resistor, and this one resistor is connected parallel in this these capacitors, and all is connected with the series with this resistor. And so we have the two which is connected with these resistors, and these two is connected with the value of this resistor, and 1 by omega j is connected with capacitors. So because we have the 1 farad here, so we have just j omega because we multiply by 1. And so we have the current here. And when we have here the current, we can calculate the current I1 using the current divider for this. And as a result, we obtain the output voltage. Output voltage is this current multiplied by this resistor. So we know that we have here the relationship between voltage, input voltage, and the output voltage. Okay, and we know from this that omega 0 is equal to, because here is the omega, so we have the omega 0, and we can put the omega in this one. So the individual components of the output due to the components of the input source. And now we notice that the impedance, its impedance of reactance of this capacitor is changed because the frequency is changed. For example, for the fundamental frequency for omega 0, we obtain here the 8, but we must be careful because for the third harmonic, we obtained another value here. So we separately calculate the voltage for the fundamental frequency, and we also separately calculate for the harmonics. And when we have the value, you can write the equations for this. So we have here the magnitude and the phase for the first for the fundamental, and the third, fifth, and seventh harmonic of signal. Okay, and another example is connected with the power, and so now we should determine the average power absorbed by network, and we have the equations which describe our source. So we see here the average value, the DC value, but for DC is equal 0 in this circle, because for the 0 frequency capacitor is open. Capacitor is open for DC. Okay, and now we examine this circuit for first value of omega. We have here the omega equal 377 and harmonics of this omega, and the second harmonics of this.
Okay, and at this omega, we calculate the reactance, capacitor reactance and inductor reactance, and we obtain such value. And we make now the same for this omega, for the third harmonic, for the second harmonic, and I obtain this results. Of course, when the frequency is decreased, the impedance of capacitor is decreased, and it is the difference from the inductance. Okay, so we have this value. Of course, resistance is constant and is insensitive to frequency. Okay, and now we can calculate the current connected with the first harmonic. So we have the amplitude and phase here, and here we have just the resistance and impedance connected with the inductance and with the capacitor. And the same in the same way we can calculate the current for omega for the second harmonic. Okay, so we have here the currents for this, and now we can write as a t function of this, and the power absorbed by network using the previously solved equations. We have here the voltage. DC voltage is equal 42, but here we have the zero current, and for the first harmonic we have the voltage 16, and we multiply by the current and by 2 the amplitude current, and now we must calculate the angle. So this is the difference between voltage. For voltage we have the angle 14, and this is the angle for the current. So we must subtract this, and this is this part is connected with the second harmonic. So we have the amplitude of voltage and the current, and here we see the differences in the angle between voltage and current. Okay, and as a result, we obtain that the power absorbed by this network is equal 7.05 watts. Okay, and signal RMS value. The RMS value, any signal, was given by such equations, and when we have the Fourier coefficients, we can try to express the RMS value using the Fourier coefficients, and so instead of this function, we can put here this value, and we separately divide it to the minus part, and for the n more than 0, and the average value, and as results we can change this one into the multiplication by 2, this one and this one, because we take to account only the ABS value here, and as a result we obtain that the 2 multiplication by the modulus Cn is equal dn RMS. Okay, so we can calculate the voltage and the current directly from these coefficients. So it could be useful when we have, for example, a spectrum, and we know the voltage, and directly from the spectrum we can calculate the power. So thank you for your attention. So I'm sorry for this problem with the at the beginning with the Zoom, but I'm not. I don't know about the email. That's that when I want to send you the email, there will be some problems. Maybe at the next week I make previously the email earlier for this. Because the invitation is not a good idea for me, because when I use the traditional form of this, I can observe on the another computer what you see in at the moment, and there is the one case when I think that all is okay, but people don't see anything because it is the error of the Zoom. So maybe it will be better the next week. So there was the question about the exam, because some of students are, for example, abroad. We still don't know about the work in the university. Yesterday I talked with the prorector, and there is some regulation about some regulation connected with the laboratory. Maybe as soon as possible we know about this, when we can return to the laboratory. Of course, not all, because few laboratories it is possible to make online. I don't know about your laboratory, but in the details. But several weeks ago, I was talking with Bogusz, and I know that's he tried makes this laboratory online, but for you, it's I think it's more interesting is the exam. For example, from the lecture, and I talking with Grzegorz Dudzik about this exam, and we are thinking now we are thinking about the online test, but so it is maybe it's a situation it will change, so we don't know exactly now what will be the form, but maybe not for all students, maybe for part students which are on the abroad. It is a good idea, but we will see. So please be patient. When I know something new, when I have a new information, I give you, for example, by email or in the next week. So thank you for your attention. So I believe that after this week, when we see the first slide, we can guess what is the type of the signal. Of course, the fundamental frequency is 1 megahertz, but you see not all harmonics here, and so it is the
additional information for you. Okay, so thank you and goodbye.